So this is the outline in front of you. Right. So what is geometry, right? While you already know what is geometry, we want to represent shapes from the real world, or the shapes that we are interested in doing some analysis on, right? So so that's why we want to represent it digitally, right? Usually, if we capture a shape from the real world, it has to be sampled before we digitally represent it. And I can give you examples. Any digital signal has to be sampled. The audio that you hear. So if I have to record my voice and play it back, it has to be sampled, just like you sample signals. So you sample it at regular intervals, and and then you reconstruct it when you want to play back, right? Anybody here from electrical ECE electronics background, they would know there is a well-known theorem called the Shannon's theorem, right? That tells you what should be the rate at which you want to sample a signal to accurately to reconstruct it, represent it, right? Similarly, for when it comes to shape, uh, we want to make sure that we sample the geometry um, dense enough so that we can faithfully reconstruct it and do whatever analysis we want it to do, right? So therefore, sampling is very important. If there is very little sampling, then you cannot hope to recover certain parts of the geometry. For example, the bunny mesh that you see here, right? A bunny that is represented by a number of triangles uh, joined together. If I do not sample the ear, one of the ears of the bunny, then there is no hope of getting it back. Or if I just have one point representing the ear and a lot of millions of points representing the body, I can't hope to get the ear back, because the ear is a very fine geometry. It's a high frequency, well, relatively higher frequency detail when it comes to the body of the shape. So you could assume that, think about the Fourier representation, right? In the frequency domain, and you might remember that there is the DC component of any signal, and then there are the higher frequencies that add detail to the signal, right? Similarly, here you could assume that you have the overall shape of the bunny that may look like an ellipsoid, and then you add more and more detail on the surface of the bunny, and those are high frequency detail, right? So in a way, you could think that a shape can also be split into various frequencies, and I can do an analysis similar to what I can do on one-dimensional signals. So that's that is to stress that if I do not sample a shape well enough, I cannot recover the details appropriately, right? So sampling is very critical when it comes to digital shape capture and representation, right? Now, well, there are already a few representations that you can use to sort of store your, or keep your shape in the form of digital shape, right? And primarily three types of representations. Explicit representation, which is to say that I represent the shape as a collection of points or a collection of triangles that are um, sewed together or joined together, they touch each other. Or let's say piecewise polygonal surfaces. So instead of triangles, I could have quadrilaterals, pentagons, or any polygon that you wish. This is explicit representation, or otherwise also known as the discrete representation, right? And over here, I explicitly say that this is my triangle or points, and the geometry is supposed to be some surface that passes through these elements like points or triangles, right? Now with points, there are gaps in the shape, right? Because however high my density is, there is always empty space. and I can see through, right? Because a point is a zero-dimensional entity, so I can see what is behind. Whereas in a polygonal or a triangle representation, which is the mesh representation, I can't see through because the triangles cover up, right? Also known as a tiling. They are a tiling, right? So they tile up. So, but anyway, this is all explicit geometry, and there are many algorithms that can convert point clouds to meshes, and we will look at a couple of such approaches in tomorrow's session, right? And these are some of the very well-known techniques. The other type of representation is called the implicit representation. Now, an implicit representation is like a scalar field, and I will explain in more detail what is a scalar field, but you could assume that you could for now think of it as for every point in the space, right? A point in the space can be thought of as a three-dimensional point, right? It has x, y, and z coordinate. So for every point in the space, if I keep a scalar value, just a value, okay, a number, that is a scalar field, right? So it's a mapping, it's a function that goes from R3, which is my XYZ space, to a scalar value, R3 to R, right? And that's why it's called a volumetric scalar field, that is, it's a volume. So to give an example, if you think of the room where you are sitting in as the space, as the ambient space, then, and let's say the air conditioning is on and it's very hot. So naturally, there's going to be a gradient, temperature gradient in the room. Near the air conditioner, it's going to be very cold. The air is blowing. And let's say, where you're sitting, you're sweating, so it's hot. So there is a temperature gradient. What we could do to model this temperature gradient is to imagine that at every point I'm able to measure the temperature, right? So the temperature is a function the temperature measured as a function of the space, the coordinates. So temperature T, the function of XYZ, has some temperature value in, let's say, degree Celsius. So that's a scalar field. Okay. Similarly, so then if I have this scalar field of temperature, then what can I do with it? Let's say you are interested in finding out where should you sit so that at least you get a temperature of 20 degrees Celsius, right? Let's say you want 20 degree, you feel 20 degree to be a comfortable temperature. What you could do then is that you could create a level set of this temperature function at 20 degrees Celsius, which is going to tell you where all in this room you get a temperature of 20 degrees Celsius. And then you can figure out that, let's say, there is some point on the floor that hits this 20 degree level set or iso contour, then you sit there and then you're guaranteed to get 20 degrees Celsius over there. Okay, so that's implicit functions in very short. Today is the day to sort of discuss that, and I'm going to talk to you about it in more detail. One very highly used implicit function is the signed distance function or the signed distance field, which we will discuss, right? But like you model temperature, like I discussed how to sort of represent temperature in the room, you could also represent any shape, right? And any shape that you could represent, for example, the bunny, and then there is this toy, can be represented in the implicit form. By the way, this the toy that you see on to the top right, besides bunny, has a very nice history. This has been captured from a real toy, and the way it is captured is using the technique known as multi-view stereo. And I can if there is a there is this thing here, I can probably also write here. If there is a chat box, I can, in between I can write the text box. Is there a text box here? I don't see it here. So there's a Q&A, but anyway, Anyway, it's called.
There is this chat symbol besides the list of participants. I think bottom right corner.
Yes, I got it. Thanks. Right. So this is called multi-view stereo reconstruction, and some of you might have seen it in action, but the idea is very beautiful. Is that you have an object, you take a lot of photographs from different angles, right? And these photographs have to have a considerable overlap. That is, the parts must be seen in at least two photographs. And you do that, you circle around the object, take a lot of photographs, and then you give it to this multi-view reconstruction algorithm, and it will take all of these, register them into this frame of reference, and calculate 3D points and the color values, right? So what you see in the toy here is basically a multi-view reconstruction of the toy from photographs, and I have deliberately not pasted here the mesh model, but it's a point cloud model. Okay, I have a question. Yes, Vignesh, please go ahead. Speak it up.
Okay, the explicit and the implicit representation that is mentioned here, it is in terms of the function, it is explicit or implicit function, or is it like?
Yeah, it's the same concept. Yeah, it comes from concept of implicit function. So an implicit function is of the form f of x, y, z. It's an implicit function, right? And an explicit function y equals to fx, right? So if you're talking from that perspective, yes, you are right on track. Implicit comes from using an implicit function to represent the shape.
Oh, thank you.
Yeah. All right. Right. And then another quite important representation is called the parametric representation. And I believe you have already had a session perhaps yesterday about parametric representation, where we use a curve or a surface with the help of parameters, right? And it's yet another very powerful way to represent surfaces. And the nice thing about parametric representation is that it can give you a very smooth representation, right? So these are the three primary representations, classification of representations. Any quick question before we move ahead? All right, so let's talk more about implicit representation, and tomorrow we'll talk about discrete or explicit representation. So what is an implicit representation, right? So it's an implicit function is defined as a function f applied to a point P, let's say in R3, in our cube, which is our ambient space, 3D space, yielding a scalar value that belongs to the, it's a scalar value, so it belongs to R. As an example, let's take the circle as an example, or I would say a disk as an example. What is the difference between a disk and a circle? A disk is a filled circle. So there is a disk is a solid, right? So there is an interior of a circle. And if you fill it, then it is called a disk. And a circle is the boundary of a disk. Okay, so let's say I want to represent this circle in the implicit form. So somebody tell me what is the how do you usually represent this circle? What's the equation of a circle? Somebody?
X equals y square is equal to r square.
Right. So a circle centered at the origin with a radius r can be is given by x squared plus y squared equals to r squared. Right. That's great. Thanks. So that's my equation of circle. But then if I ask you, that is all fine. But if I ask you to plot it, how would you plot it? I mean, how do I get some points on this circle? How do I get points on this circle? Anyone?
We will fix x coordinate and then find the y coordinate.
Yes, but how would you find the y coordinate again? What would be y? So you're saying that you convert it into an explicit representation, but there is a problem,
Yes.
slight problem with that. How do you do that? And what is the explicit form?
Explicit form is y is equals to plus or minus root r square minus x square.
Great. Yes. Thanks. So in a sense, you had to cut the circle into two parts, two halves, so that each half is a function. That is y equals to some f of x. In which case it is plus and minus of square root 1 minus, r square minus x square, right? So then now you could sample easily and done. This will give you some points on it. There is one more, so that's explicit representation. Now there is also a parametric representation of circle. Anybody here knows what is parametric form of a circle?
Is good R cos R
Sorry.
cos theta. Using theta, we can do that. So, yes.
Right, r cos theta, r sin
Theta.
theta, right? So where theta is the parameter that goes from 0 to
0 to 360.
0 to 2 pi. Yeah. So that's my parametric representation. Now, when it comes to implicit representation, I use the form x square plus y square minus r square equals to 0. I can move r onto the left hand side. So my f of xy here becomes x square plus y square minus r square. And then the circle in this case, S, is set of all the points xy for which fxy equals to 0, right? This is defined in terms of the locus of points that move on the circle, right? So all points x comma y that satisfy this equation x square plus y square minus r square belong to the circle. Now, what else can you say about this implicit form? Well, there are more things, there are more goodies with when it comes to implicit representation. And one such very nice thing is that I can precisely tell which points are inside and which points are outside. If I just evaluate this form, any point that evaluates to negative value is inside this implicit representation, implicit form of this curve or surface. Anything that is greater than 0 is outside, right? So if I tell you that, okay, there's a point x naught, y naught, tell me if it is inside, outside, or lies on the circle. Very quickly, you will plug that point into the equation, into this expression and evaluate whether it is equal to 0, less than 0, or greater than 0. And that will immediately tell you where it is, right? So that's the implicit form. We will take more examples, but is the basic idea clear to everyone? That is, an implicit surface is defined in terms of in terms of a set of all the points that satisfy a particular function f. Okay. All right. Now, an implicit function f may be split into two parts. Now we are coming to the skeletal modeling part. How do I model something, right? I want circle is fine, or maybe straight line is also fine. And before I move to this, let me also very quickly tell you a little more about different forms. So let me allow to share my screen. Okay. See this, right? So what happens when I have a straight line? The implicit equation of a straight line is given by ax plus by plus c equals to 0. So my f here, f of x comma y, is ax plus by plus c, right? And in this case, there is no inside outside, but you could imagine that if this is the R2 space, this is R2, then the straight line sort of partitions the space into two halves, right? The negative half and the positive half. And of course, the boundary of that is the line itself, right? And this is true for every implicit function, is that it partitions the space, whichever space it is, R3, R2, or whatever, into into two partitions. So in this case of circle, you have f less than 0, f greater than 0, and depending on the line equation, you will have one part f greater than 0 and one less than 0. You can always invert this negative positive business by inverting by negating f, right? But it is clear that there would be one partition with it which is positive, the other one which is negative, right? So we looked at the circle, which is f equals to x square plus y square minus r square. And what else? We also looked at the straight line. Anything else quickly that you want to ask me about the implicit equation before we move forward? Yeah, I think this is good, right? So in any case, always the surface, and the same is true in 3D as well. You have a function fxyz, and that's my implicit function, and this is always the surface is the set of all the points xyz, such that f of xyz equals to some k, right? Now usually k equals to 0, but you can also have a non-zero k, right? And as we will see later today, these different k's are known as the level sets of this implicit function. So when I say k equals to 0, this is the 0 level set, right? So these are the different level sets of this implicit function, right? So k equals to 0 is the usual a usual level set that we are interested in, but you could have anything in k here. So if generalized, that would be my surface representation, right? And some of you might have observed that we have lifted, in order to represent a sort of a 2D shape or a 1D shape, we lifted the dimension to one higher, right? The implicit function is always one dimension higher in this case. Anyway, so let's questions asked me, otherwise we just okay. So right, so that's the definition of my implicit functions. Now, as I said, an implicit function may be split. When I want to do a modeling, I want to split it into a distance function and a fall off filter function, right? Now, two things here. A distance function is an implicit function. Basically, what it says is that for every point, it will give me a value, right? That value is the distance value measured from a certain surface, right? So now, if I am on the surface, the distance value would be 0, and as I move further away from the surface, the value will increase, right? And I'm talking about the shortest distance to the surface. I'll discuss more about it, but for now, a distance function is a function that maps R3 to R, where R is a distance measured from some surface, right? Now, then there is a fall off filter function that I want to design, because I may not want the distance function as is, right? I may not want a increasing distance from the surface, but I might want to modify it. So this fall off filter function, what it does is that it modifies the distance function to something else, something that falls off. It starts off very high and then it falls off, right? So my final implicit function is then a composition of the distance function and the fall off filter function, and it is given by g of d, right? So that's my implicit function fi. The nature is still the same. Gi is a function that maps scalar to scalar, so r to r, and then d is a function that maps r3 to r. Okay, so the eventual result is still the same, that is f is a function that maps r3 to r. And the field values as a result are maximum at the skeleton. And then these fall off to a certain distance from the skeleton with finite support. And if you, so you have a certain shapes, right? So-called skeletons. And then let me jump a little forward. And where do I have the skeletons? No, but let me quickly talk about skeletons here. I think I don't have it here, but let me just quickly tell you what are these skeletons. Right. So this fall off filter function modifies the distance field, but before that we need to define what is a skeleton, right? In our case, a skeleton is any shape that I can use to define a implicit function. For example, it could be a line segment, it could be a point, it could be a rectangle, right? And let's take an example when I want to define a distance field with respect to a straight line is for any point in the plane, I measure the distance, perpendicular distance from this skeletal element, which could be a line, a point, or any 2D shape, right? You could, or it could even be a curve, right? So that's my distance D, right? And for example, if the point is here, then my shortest distance is going to be this, right? It would not be perpendicular, and then you probably would have guessed by now the recipe for this distance is for a line segment. A line segment you can imagine that would partition the entire space into 3 regions, 1, 2, and 3. It is only that if a point is in region 2, that the distances would be, the shortest distance is going to be the perpendicular drop down to this line segment. If the point falls in region 1 or region 3, then it's the distance between that closest end point from that line. And for example, this one here, right? So that's how you calculate distance to a line segment. A circle, a point is very easy. So if this is, if this is my point, then the distance from a point to point is very easy. You just calculate the distance between the two, right? Similarly, if I have a point here, I simply calculate this distance, right? And for a square sheet, the way it happens is, you can think of the square sheet as being dividing the plane into multiple domains. And did you guys cover offset surfaces? Yes, no?
Yes, I think they were also introduced quickly to medial axis and Voronoi diagrams.
They have already been introduced?
Yes, but quickly though. Professor
Okay,
Ramdas
I have,
introduced Voronoi diagram,
yes,
and today they were introduced to medial axis.
okay, I will anyway have that in context of meshes tomorrow. So anyway, that would be a recap for them. But then, if I talk this in terms of the offset surfaces, then you can say that, look, if I have an offset surface of, like this, that these are going to be circular caps. So any point, basically what happens is that any point that is in this domain is going to pick its distance from this vertex, from this endpoint. Any point which is here is going to pick the distance perpendicular to this line segment. And you got the idea. And then this offset surface is a level set of the distance field of this square rectangular plate. But anyway, maybe I'm confusing you guys with this offset surface. But you know that there are these two types of regions. One that are computing this shortest distances from the corners, and then the other ones that compute the shortest distance from the end from the line segments of this, right?